This video is about UJT. UJT means Uni Junction Transistor. UJT is also a solid state semiconductor device similar to SCR that we discussed in the previous video. Solid state semiconductor device means the device operates with the movement of electrons or some other charge carriers through the material. And the material is a solid material, which means the device does not contain any moving parts. So there is no mechanical motion in the solid state semiconductor devices. We have various types of solid state semiconductor devices, but UJT comes under thyristors. The figure shown here is the symbol of UJT. So UJT is a three-terminal semiconductor device with two base terminals B1 and B2 and one emitter terminal. And you can observe emitter terminal is nearer to base terminal B2. This figure shows how UJT is constructed. You can observe it has an N-type silicon semiconductor bar with an electrical contact on each end. These two connections make two base terminals B1 and B2. And there is a P-type material near to base 2 with an electrical contact. This electrical connection makes the emitter terminal. Because this p-type material is near to base P2, a p-n junction is formed between a p-type emitter and the n-type silicon bar. Now you can understand why UJT has the name Uni Junction Transistor, because this device has three terminals and one p-n junction. It has one p-n junction, so it appears like a diode. But you can observe two base leads are taken from one section of the diode. That is why this device is also called as double-based diode. The N region here is lightly doped and the emitter is heavily doped. So, note that when the emitter terminal is open, the resistance between the two base terminals is very high. Now, let us understand how UJT operates. With no voltage at the emitter terminal, that is, keeping the emitter open, apply a voltage of VBB across the two base terminals B2 and B1. Now, obviously, potential gradient gets established along this N-type silicon bar. And because emitter terminal is located closer to base B2, major part of the voltage VBB appears between emitter terminal and the base terminal B1. And since there is no voltage at the emitter terminal, but there is voltage at the base terminal B1, a reverse bias is established on the PN junction and the emitter current is cut off, but a small leakage current flows from BT to emitter due to the minority charge carriers. That is why the device is in the off state with emitter open case and when voltage VBB is applied between B2 and B1. Now let us apply a positive voltage at the emitter terminal. From the previous case, we already know that a part of voltage VBB has caused reverse bias between the terminals emitter and the base B1. So now as soon as we apply VE, the device doesn't get on because there is an existing voltage V1 that causes the reverse bias of the junction. So reverse bias gets maintained until VE is less than V1. When applied voltage crosses V1, the junction becomes forward biased. So holes are supplied from the P region into the N-type silicon bar. But since B2 is positive with respect to B1, the holes move towards B1. Because holes are attracted towards the B1 terminal and there is increase in the number of holes in the emitter to B1 region, resulting in the decrease of resistance of this section of the bar. This decreased resistance causes the internal voltage drop from emitter to B1 region to get reduced, causing emitter current IE to be increased. Now you can see the device is exhibiting negative resistance characteristics. That is, a decrease in the voltage causing the current to increase. Now, as more and more holes are supplied, a condition of saturation is reached. Now, at this saturation point, it's time for the emitter power supply to limit the emitter current. And now you can conclude in this case that the device is conducting right, so the device is said to be in on state in this case. Now, after understanding the working of UJT, let us understand the emitter characteristics of UJT drawn at a particular value of VBB. First, when you increase the emitter voltage from 0, we know that the device maintains its reverse biased state, so a small leakage current due to minority charge carriers flows from terminal B2 to emitter. So this leakage current is represented in the cutoff region. Now, when VE reaches a definite value, the emitter current IE starts to flow and increases until the peak Vp and Ip is reached at point P shown in the figure. Then after point P, due to the more attraction of holes towards the base terminal B1, there is a sudden increase in IE with a small increase in VE, and this sudden increase in EE causes a corresponding decrease in VE, which exhibits the negative resistance region of the device. This negative resistance region continues until the valley point V, and once the device reaches the valley point V, the device enters into the saturation region. So this is how the characteristics are drawn according to the working principle of UJT. This is the equivalent circuit of UJT. From this equivalent circuit, we can derive certain important equations. The total resistance of the silicon bar is called interbase resistance. This interbase resistance is the sum of the resistance of the bar between emitter and B1 region, that is RB1, and the resistance of the bar between the emitter and the B2 region, that is RB2. So, RBB interbase resistance is equal to RB1 plus RB2. The intrinsic standoff ratio of the device is given by the ratio between the voltages V1 and VBB. This standoff ratio can be obtained by applying the voltage division principle. So V1 is equals to RB1 by RB1 plus RB2 into VBB. So eta is given by RB1 by RB1 plus RB2. From the equivalent circuit, we can easily write the peak point voltage of the UJT. That is when UJT becomes on. So Vp is equals to eta VBB plus Vd. This concludes the topic of Uni Junction Transistor. If you like the video, subscribe to my channel and like and share the video. Kindly help me to help you.